All right, in section 9.4, there's several more examples of applications of using vectors. And if you look through the completed notes that are posted on Canvas, you can see more examples, but we're just going to do one example dealing with equilibrium forces since we already saw an application problem in the last section. So with forces, right, I could run over to you and I could push you down, right? So the force of me pushing on you could knock you over. But you could also have situations where there's multiple forces acting on an object or on a body, and the body is the forces are in equilibrium with each other, so that something like a mountain climber could be basically at rest, so just kind of hanging there, not falling down or anything. That happens if the sum of the x components of the forces is 0, and the sum of the y components of the forces is also 0. So for our example, like I said, we're looking at a mountain climber. If he's 165 pounds, that's one force pulling down on him. If he's suspended, though, by a rope, all right, in this case angled 60 degrees from the horizontal, that's going to help hold him up, right? And then also, okay, so it says if T is the tension in the rope, and then F is the horizontal force at which the climber pushes on the side of the cliff, we want to find the magnitude of the two forces, the tension in the rope, and then the force that he's pushing on the cliff. So we have three forces. We have the tension in the rope, right? Him pushing off of the cliff, and then his weight pulling him down. What we can start by doing is creating a free body diagram. So we'll replace the body. In this case, it actually is a human body, but in many other applications, it's not really a person, it's something else, with a point, and then use vectors to represent all the forces. So we have the rope, right? And we know that it's 60-degree angle there. We have the force from pushing off of the wall, right? The wall. And then we have the weight force going down. What we want to do is figure out if he's in equilibrium, if he's in equilibrium, right, that the forces are in equilibrium, what is the magnitude of the tension force and the magnitude of the force where he's pushing off the wall. So we're going to organize everything in a table. The magnitude of the tension force, well, we don't know that, so that we're going to call that T. The magnitude F, we don't know that either, but we do know the magnitude of the weight is 165, so that's his weight. The angles, we know some of these, right? Actually, we know all of these. The rope, that's 60 degrees. Vector F is 180 degrees. The weight vector going down, right, that would be 270 degrees in standard position. And then we can represent all the components. Remember to find the x component, you take the magnitude times cosine of the angle. So this one would be T times cosine of 60 degrees, which ends up being 0.5 T because cosine of 60 is 0.5. This will be F times cosine of 180, which is, cosine of 180 is -1, so this is negative F. For our weight, we're going to have 165 cosine of 270. Oh no. All right, I have to grab a new pen real quick. All right, so we have 165 cosine of 270, which is going to be, let's see, cosine of 270 is 0. Okay, so this is 0, which makes sense because the weight's pulling them straight down. So the x component, it's not going to affect that. That's going to be 0, right? The y components, we take the magnitude times sine of the angle. So this one would be T times sine of 60. We'll have to round this one. So if you plug that into the calculator, you get about 0.866. So 0.866 times T. Next one's going to be f sine of 180. That's going to end up being 0. The next one will be 165 sine of 270. Sine of 270 is -1, so this ends up being -165, which should make perfect sense because the weight's pulling down 165 pounds in the y direction. All right, so since the man in the problem is at rest, the forces are in equilibrium. Therefore, the sum of the x components and the sum of the y components must equal 0. So we can set up equations. So if we add all of these values together, it's got to equal 0. And if we add all of these values together, it has to equal 0. So our equations that we get from that are 0.5t minus f plus 0, that doesn't matter, equals 0. And then 0.866t plus 0 minus 165 has to equal 0. So we look at these, which equation can we actually solve right away? Well, we can solve the equation that only has one variable in it, right? We can figure out what t is. So let's start with the second equation here. If we add 165 and we divide by 0.866, we get that t is approximately 190.5. All right, so this is in pounds, the tension in the rope. All right, now we're gonna find F by taking this t value and substituting it in. So we're using substitution. 0.5 multiplied by 190.5 minus F equals 0. Solving here, if you add F over, you see that F is actually equal to 0.5 times 190.5. So half of 190.5 is about 95.3 pounds. All right, and that's it. So there are 2 more examples of these equilibrium problems in those completed notes. If you look at the next page, I would encourage you to do that as well. Actually, one of them is the same or maybe it's very slightly different than one of your homework problems. All right, toodaloo.